Word problem number 3 for our differentiation review refers to exponential growth and decay. Do you remember this from earlier in the semester? Feels like I was just making a video on it, but looks like it's been a month or so. So let's just double check that we remember. P of t is equal to PE to the RT. I call it the PERT function. Imagine why. And they tell us some information. They tell us there's 200 cells and they grow to 360 cells after half an hour. So the way we would write that is 360 equals 200 e to the r times 0.5. Big shocker there. So divide the 200 out, and that becomes, let's see, 360, so that's 36 over 20, that's 9 over 5, so it's going to be 1.8 equals e to the r over 2, if you will. Let's take the natural log of both sides because there's an exponent in the there's a variable in the exponent, and that allows us to say ln of 1.8 equals ln of e to the 1.8, that's not true, r over 2, sorry. And that natural log function lets us bring the exponent out as a coefficient. That's why we do it. So you can say ln of 1.8 is equal to r over 2 natural log of e. And that's just 1, so that's gone. Let's multiply by 2 up to here. We can say the rate of growth, not that we've been asked yet, equals ln of 1.8 times 2. So let's put that 2 in front. 2 ln 1.8, like that. That's going to come out to about 1.1756. That's good there, I think. So now we have a function. We can say P of t equals 200 e to the 1.1756 t. And that brings us down to only a time variable, so that's great. And part A says find the number of bacteria after t hours. That's this function. Part B says tell us how much there is after 4 hours. And all they're asking you to do here is put in a 4. And when I type in a 4, I just plug in these values. What do you get? You should be doing this on your own. But I can tell you that I got 22,060. It's a lot of bacteria after 4 hours, starting from only 200. But that's how bacteria work. Okay, so what about the rate of growth after 4 hours? Did you see that? Find the rate of growth after 4 hours. That actually requires math because they're asking us to start from P of t equals, let's just use the one up there. I can take that number away. They're asking us to take this formula and take the derivative of it. So we want dp dt like this. And we can take the 200 out because it's just a value. But here's our function. Well, what's the derivative of e to the something? It's e to the something. So that's going to look the same. 1.1756 t times the derivative of the inside, another 1.1756. That's our dp dt. Well, if I take that, and I know that this already is, what was it, 22,060 times this, we don't even need to recalculate with the 4 and such because we have it from last problem. So it would be growing at a rate of 25,940 per hour. Now it'll actually grow by more than that because in 20 minutes there will be more cells that are growing with it. But at this exact moment, this is its rate of growth, which means it's going to more than double in an hour. That sounds about right for bacteria for sure. What else do they want? When will the population reach 10,000? So what value is that? That's this here, this P of t. So we'll say 10,000 equals 200 e to the 1.1756 t. Divide by the 200, cross those zeros off. What's 100 divided by 2 is 50, equals e to the 1.1756t. And again, in the exponent is the variable, so we natural log both sides like this. And you will take the t out as a consequence, so we would get ln of 50 equals t ln of, well, we can take out more than just the t, right? We can take out the coefficient with it too, 1.1756t e, natural log e, like that. Natural log of e is equal to 1. So now we just divide and we get t equals ln of 50 over that. And that should compute out to about 3.33, and that's in hours. So in another 3.33 hours from start, we're going to have 10,000 bacteria. And that's all they're asking for here.